Hi everyone, my name is Kara and Treasure, and I'm here to present our project named the Multimodal Edge AI Partial Discharge Diagnostic System that aims to detect, classify partial discharge, and also locate the partial discharge in high voltage electrical equipment. In this presentation, I'm going to introduce two models that I trained on acoustic data that contain partial discharge. So the contents of these presentations will includes an introduction, a dataset description, the model architecture and explanation, the results that I obtained, the conclusions that I drew, the limitations I faced, and the acknowledgements. So the dataset I used consisted of over 8,000 files that contained partial discharge chaps and white Gaussian noise sampled at a rate of 96 kilohertz for a duration of 50 seconds, whereby each sound was played for a duration of 10 seconds, 5 times. This sound was collected across 90 locations on 18 SATA coils using a 32-channel MEMS microphone. The information was captured in the naming of the files, whereby the naming captures the configuration number, the fault location number, the audio file type, and the channel number. The audio files are processed into scalograms. Scalograms you can understand them as fingerprints of a particular sound, whereby each sound has a particular fingerprint, has a unique fingerprint. So these scalograms were processed into a 5-dimensional high dimensional tensor, which is a series of numbers but are in a 5 dimensions, whereby the shape was had the batch size, had 8 as a batch size, 1 as the color, which means we're using one particular color, that is the grayscale. We had a spatial dimension of 32. The 32 channels represented the depth. We had the frequency dimension, which represented the height, as you can see in this image, and we had the 1200, which represented the time in which the wave was recorded, which was the width, which represented the width. So the physics features of rise, that is how high a signal wave rises. Kurtosis, which means the peaks, the number of, which means the number of peaks in a particular sound wave. The central represents where the energy is concentrated, and the skew that represents the shape of the sound wave were processed into a 2-dimensional list. So these features are used to inform the model. So the model may not just choose the neural network, it may also pick from the real life physics aspects of a sound wave. So you can imagine the input data as a cube, as you can see below, whereby, as you can see in the video, whereby the depth is the frequency, the depth are the microphones, and then you find the frequency distribution is represented as the height, and then you find 1200, which is the width. So these are stacked together to form a batch size of 8. So the first model I trained was the partial discharge neurosymbolic net model. The purpose of this model was classification between partial discharge, white noise, and the chap signals from acoustic data. So it consisted of 3 branches. So one of the branches was the neural perception branch, which was fed by one source of knowledge. That is whereby a 3-dimensional convolutional neural networks learns patterns from acoustic scalograms that are derived from the data sets. That was the first source of knowledge. And the second source of knowledge was physics knowledge, which informed the symbolic branch. And then all of these branches were then combined into a fusion classifier branch, which to get the final prediction. So this was the model architecture, and this is how the different tensors changed as they went through the model. So initially you find the 5-dimensional tensor that had the batches that fed into and has one color channel, the 32 microphones here. The sound that was captured from the different 32 microphones, that's like one layer. And then you find the frequency scale and also the time taken. So after passing through the first residual block, you see that the color channels are increased or expanded to 16. On expansion to 16, it means that more audio features. It looks at it goes through this tensor, a 3 times 3 kernel, or you can say 3 times 3 cube, goes through this tensor, through the values that are in the tensor, the mathematical values, and multiplies each of these tensors, and then expands the the color channel from 1 to 16. That expansion represents the identification of more audio features. So if you look at the residual block, when you input a tensor, so this tensor has been inputted, this convolutional channel, it applies that kernel which goes step by step. We used a stride of 1, which means it goes step by step, multiplying the numbers in the tensor to produce the second tensor, the output. And this output is then fed into the batch normalization layer. So with this multiplication, you find that some values are really high and find some values are really low. So in the batch normalization, we normalize these numbers, which means we put them in the same range so that you don't have higher numbers affecting the training more than the lower numbers, which may also affect the speed at which the model lands. And then we find the rectified linear unit. What it does, it introduces non-linearity into the model training. How does it do it? It changes all the negative values that have been produced from the convolutional layer and the batch normalization layer and changes them to 0. Rather than having a linear layer, it enables the model to learn the different curves or the different complexities of the data as training goes on by converting the negatives to 0. So after that, in the residual block, you find it goes to the second convolutional neural network, which does the same thing. It gets this block, this 3 times 3 size block, and it computes the different numbers on the tensors. So after computing different numbers from the tensors, it again goes to the batch normalization. So after the batch normalization, we find that we're going to the squeeze excitation attention block. So the use of this block is to learn the different weights that inform the model, and from learning the different weights, it recalculates them in order to increase the weights for more important features and to decrease the weights of less important features, so that the model can focus on more important features that may lead to better predictions. So the first thing it does, it flattens the block. So remember we had fed a 3-dimensional block or a 5-dimensional block. Yes, it flattens it into a 1-dimensional block using average pooling. So by getting the average of all the numbers in order to learn the global features. So once it learns these global features, it goes to the first linear layer, which can reduce these features to focus on the most important features. And then after focusing on the most important features, it goes to the real layer, which again, but explained, it does the real layer does it introduces the non-linearity into the model. So after that, we go to the second linear layer, which then expands the features to its original shape. So with this original shape and the land weights are then taken through the sigmoid gates, which computes the weights into a range of 0 to 1. So after these weights have been computed, they are fed. These weights are then used to scale the features. So you multiply each of the features with each respective weight. So you may find some features being scaled and some features being scaled upwards, others being scaled lower, downwards, depending on their importance. So the next stage is feature. The next stage after this will be the feature addition. So remember, in a residual block, initially the original shape of the tensor is stored as the identity. So this is what, once it's stored as the identity, it's then added to the new newer calculated shape, and this is done so that the model does not forget how the sound looked like originally. So this helps when you find that the convolutional layer, the information extracted from the convolutional layer was not that important, so you're able to keep the original information. That's why we need the identity or the shortcut connection. So from then you take it through the linear rectifier activation, and then you output a tensor. So that's what happens in a residual block. So after each residual block, you go to the maximum pooling. So what it does for it halves the spatial dimensions. So you see the channels being increased, say by doubling the size, while the spatial dimensions are being reduced. So you see the 32 right now we're having 32, now we're having 16, each of them being half. So you go through all these blocks until you reach the global average pooling. So at the end, you'll be having you can have a scaleogram that's having a tensor of this shape of 8, 128, 4, 150, but this tensor is still huge and may need a lot of mathematical power in order to calculate the numbers in it. So what the global average pooling does, it forces the tensor into a particular shape that has been indicated. So you find the tensor has now been reduced to the size of 128, which represents the color channels that have been extracted after each residual block, which are the acoustic features that have been extracted. And then you find one which represents the microphones, and then you find 2 which represent the frequency, and then the last 2 which represents the time. So after this, these features are then multiplied in the fattening layer, so they're falling into a one-dimensional list. After being fed into a one-dimensional list, remember, we still have these 8 batches, so you end up having 256 features. So after having 256 features, it goes through the linear layer, batch normalization, and the dropout. What dropout does, it deactivates some neurons so that the model does not overfit, so that the model doesn't cram say information. Yeah, overfitting is when you find the model is performing well in training, but after training or in validation, it performs badly. So for the model not to overfit, we have to deactivate some of those neurons so that the other neurons can also learn the model features, or to learn the weight. So after this, we go to the concatenation stage. But remember, we also have the physics branch. The physics branch, we had a batch of 8 of the 4 features. This was the tensor shape. So these, after the first linear layer, these 4 features are then expanded to 32 features. So you go through the dropout stage again, where some of the neurons are deactivated, and then you end up with the 32 features being extracted. So in the concatenation stage, here these features from the perception, the neural perception stage, and the branch and the symbolic branch are then added together to form 288 features. So these 288 features are then reduced. So as you go layer by layer, it reduces to 128 features, then the 64 features, and finally they are reduced to a tensor that contains 3 features. So to predict the 3 classes, or the probability of the 3 classes, using by the probability of 3 classes. So as you can see, we have the fusion layer, which combines the neural and the physics outputs, and then it goes to the linear layer that features the output 128. You add the linearity, batch normalization, the dropouts, the linear layer again that feeds them to 64 features, and then you find it has then the real layer, and then you go to the linear layer that again feeds them to 3 probability scores. So what it does, it outputs those 3 scores. So how does this model learn? It learns through the forward pass, so whereby the model can takes in the output and predicts the class scores. As it predicts these class scores, the loss calculation is calculated using the process entropy loss. So this loss is then, once you get a particular loss, it is then traced through all the layers to see which weight contributed to the loss. And then the weights are then updated in order to reduce feature errors. That is optimization. So you can see that the optimization happens with the Adam optimizer that includes the weight degradation, which means it adjusts the weight to prevent overfitting or to improve the loss that has been found. It also adapts the learning rate per parameter. So in the optimization, you also find that reduce the learning rate on plateau. So when you find that the validation loss has plateaued, or that the model is not learning anything new, you can reduce the learning rate so the model can take more time in learning more features using the reduce the learning rate on plateau. So the features that were optimized, we had the convolutional kernels. Remember, the convolutional kernels with 3 times 3 times 3. That's our parameters. So we have the linear layer weights, batch normalization weights, attention parameters. And then we have the hyperparameters, which included the learning rate, the weight decay, the rate at which the weights can be reduced using the Adam optimizer, the epochs, the cycles by which the model is trained, the scheduler patience, how long will the scheduler wait? In order, when the validation loss plateaus, in order to how many epochs, will the scheduler wait in order to reduce the learning rate? Early stopping, in case the model has the same results over consistent time, how many epochs are we supposed to wait in order for us to stop the learning of the model, in order to prevent overfitting? So these were the results of the model that I managed to train. So the best model was at epoch 20 out of 50. So the train loss was When we go to the average, the train accuracy was around 98%, while the validation accuracy was around 96%. You can see here. And then for the explainable AI here, we see the scaleogram, how the scaleogram had been processed into a feature map. So this is what a feature map looks like. So within this feature map, we see, using the GradCam, we're able to see which areas of the feature map informed the model results or had the most predictive power. So after that, so these are the results. We're going to go to the second model. The second model was the PD localization model. The purpose of this model was to estimate the spatial location of partial discharge source from acoustic data. So the overview, this model consisted of three major components. We have a CNN feature extractor. We again used the physics features in order to inform the model, since we are to deploy this model in say real life settings where physics is a major influence. And then we at the third branch was the fusion regression head, whereby we had the fusion whereby these features were then concatenated, and then we're able to get a particular number or particular coordinates. So this time we're predicting coordinates. So the audio waves are then processed into scalograms, which are processed into 4 high-dimensional tensors. So remember, initially, the first model had 5 high-dimensional tensors, but this time we're looking at 4 high-dimensional tensors. This is because we are using 2-dimensional convolutional neural networks in order to train this model. And you remember initially the microphone channels acted as depth, but this time they are going to act as the colors. So you find say a particular feature map whereby the different microphones are also appearing on the same two-dimensional space, but as colors instead of as depth, because the previous one we used mainly a 3-dimensional space as well, visualized using the cube. So this is the shape, whereby 16 is the batch size, 32 is the spatial dimension, we have the frequency dimension, and the temporal dimension. So each of them 100, 1,200. Why is it? Because we are downsampled. Remember initially we had 96 kilohertz, but in both these models we downsampled to 1,200 due to the computational power needed that was available. So the physics features stay the same, but this time we're using a batch size of 16. So this is how the model looked like. This is a visualization of the model architecture. So we begin with our first tensor. And then when it goes to the first convolutional 2D network, so you find that, imagine like a matrix, a 3x3. This time it's also 3x3, a 3x3 matrix. So this 3x3 matrix it goes through the tensors that have been processed from the scaleogram. So once it goes through its tensor, number by number, calculating different values and extracting more features, you find that the channel size is increasing. So this time with the first convolutional layer, the channel size doubled to 64. So it goes through the linear rectifier units that adds nonlinearity, which I had explained before. Then it goes to the maximum pool layer, which has the spatial features. So you find the frequency and the time are being halved. And with this, we're extracting the highest. So the highest numbers from the feature maps are extracted, leaving the lower numbers. That's why you find that the spatial features for these features are being halved to pick the most important numbers. So you find the convolutional layer again extracts, increases the channel number to 128, which means that's extracted more features, which is going to the fine details of the features. So again, it goes to the rectifier unit and maximum pooling, which again halves the features. So it goes to the third convolutional block, 2-dimensional block, and then you find that the features have been increased to 256. It goes through the rectifier linear units, the ReLU layer, what it does in order to add non-linearity. And then this branch then goes the next step will be adaptive pooling. What it does, it forces the shape into the the shape into 1 times 1 for both the frequency and the time feature of the tensor. And then from at this stage, we flatten this tensor. So you find that the tensor has you may find that the tensor is of this shape. So a 4-dimensional tensor, you find it has been now flattened to say a 1-dimensional tensor, but the batches are 16. So you flatten it, and you're able to extract 256 features from this layer. So from the physics branch, you find that the 16 batches have been, and the four features have been inputted inside, and then you go to the linear layer that extracts 32 features from the 4 features, and then go to the second linear layer whereby the refinement of these features is done again, and then these 2 features, the 256 and the 64 features, are then added in the fusion and localization head to get 220 features. So getting the 320 features, they're taken through the linear layer, which fuses these features to 128. So you go to the ReLU, the dropout layer that turns off some neurons, the linear layer again that fuses these features to 64, and then the ReLU, and then you go to the output layer, which outputs the 2 coordinates which represents the location of the partial discharge. So how does this model learn? It learns through supervised learning, whereby we're using the location that has been provided in the files as our labels. And then we have the forward path where the input is forwarded through the network to produce the spatial coordinates of the fault location. We have loss computation. The loss is calculated using the mean squared error. And then we have backpropagation. Backpropagation, I explained it earlier, whereby when you get the loss using the mean squared error, you go through the upper layers in order to find which weights contributed the most to this loss, and then you adjust the weight. That is backpropagation. And then the parameters to optimize, you have the convolutional kernels and linear layer weights. The hyperparameters, we find the learning rate which was changed using the Adam optimizer, and we have the epochs. So the model was optimized using the Adam optimizers with weight degradation, which is this optimizer. So these were the output results, whereby we find the validation and the validation loss. The best results were at epoch 28 with a mean localization of 4.02, which means the predicted results, most of the predicted results were 4 units away from the actual source of the error. So the conclusions, both models achieved acceptable results, though further improvement can be achieved with the localization model. So the first model performed better than the second model. The limitations were compute power, whereby we could have used a higher sampling rate or extracted more features from the scalogram. So there was a long data processing time and a large data set that prolonged the processing time. So the next steps will be further model improvement and testing on unseen data, and also trying out using different model architectures to see where we can get the best results. My acknowledgements go to Mr. Galiwango for influencing the development of these models and influencing the development of this work. Thank you so much.